In studying multiple inheritance and understanding why it's needed, we can start from very simple examples that actually are not software examples per se, but are just analogies from daily life. Take, for example, the notion of dining car, as in a train. What's a dining car? Well, it's a place in a train where you can have a meal. So, on the one hand, it's a train car. It's like any train car. It can be made part of a train. So, in software terms, we would have commands like attach the car to the train or detach the car from a train, from its train at a station. We would have queries such as the train to which the train car belongs, and so on. But it's also a restaurant. It's a place where you have features like give me a dinner, or bring me the bill, or what is the price of this meal, and so on. Both viewpoints are equally valid if we're talking about the dining car. So in software terms, we'll say that the class dining car, if we ever had to write such a class, would inherit from both train car and restaurant. There are lots of examples of that kind from daily experience. For example, we can talk about calculator watches. We have calculators, we have watches like wristwatches, and you have some watches that also serve as calculators. They have a little keyboard that enable you to make computations. Consider the notion of a company plane. If you are fortunate enough to have a company plane, well, it's a plane. It has features like takeoff and land, and if we go to queries, it has a speed, it has a capacity, and so on. But it's also an asset. From the accountant's viewpoint, like any other asset, it has queries like current value, resale value, purchase price, and commands such as amortize it, resell it, and so on. So that's what a company plane is, and the corresponding class would inherit from both class plane and class asset, and so on. You can think of motor vehicles, which are both homes and vehicles. You can think of a trolleybus, which we can consider as being both a tram and a bus. So this is typical of situations in which we want to combine two abstractions, which is what multiple inheritance is about. And you really want multiple inheritance in the sense that you don't want to have to be forced to choose between two of these abstractions. Is a dining car more of a restaurant or more of a train car? This question has no meaning. The dining car is both. From these everyday life examples, we can move to real software examples with classes just as comparable and numeric, which are important classes of the Eiffel kernel library, a library of fundamental classes that must be provided by any Eiffel implementation. So it has things like string and array, but it also has mathematical notions like comparable and numeric. Comparable represents the abstraction total order. That is to say, the class is going to have operations like less than or equal, greater than or equal, and it represents objects that belong to a set equipped with a total order relation corresponding to these features. Another important class of the kernel library is numeric, which has operations like plus, minus, multiplication, and division. In that case, the mathematical model is that of a commutative ring, which is a structure with such operations and a 0 and a 1 and some properties like commutativity and distributivity. What's important here is that if we take objects like integers or reals, they are both comparable and numeric. That is to say, they have all the operations on the left with the associated properties of a total order, and all the operations on the right with the properties of a commutative ring. So multiple inheritance is the natural solution in that case, since we want classes such as integer, real, and quite a few others to inherit from both. On the other hand, just to avoid any confusion, this would not be a reason to merge classes comparable and numeric. They correspond to really different abstractions, as illustrated by the observation that we have objects that are comparable and not numeric, for example strings, which have an alphabetical order, so we have all the total order relations, and operations, but they're not numeric. They don't have multiplication, for example. And on the other hand, we have complex numbers as an example of objects that are numeric, meaning they have all the operations on the right with the properties of a commutative ring, but they're not comparable. There's no useful total order relation on complex numbers. So this to indicate that the two abstractions, comparable and numeric, really should be different, and then we can use multiple inheritance to combine them. This is perfectly normal and standard. Well, standard yes, but not in all object-oriented programming languages. So here it's important to mention that the solution that we've started to see involving multiple inheritance is not available in Java and in C#. The Java and C# solutions are really essentially the same. C# took it from Java, so I'm going to refer to Java in this discussion, but it really applies to C# as well. In those languages, a class can inherit from at most one class. So for classes, we have single inheritance. On the other hand, there's also a notion of interface, and a class can inherit from any number of interfaces. What's an interface? Well, in pure Eiffel terms, you can think of an interface as being the equivalent of a deferred class, but a deferred class that is fully deferred. When we saw deferred classes, we saw that a deferred class is not completely implemented, but it doesn't have to be completely deferred. That is to say, they can have a mix of features that are deferred, not implemented, and features that are effective, that is to say, implemented. Well, if we think of an interface, it's like a deferred class, but everything is deferred, so it's completely disembodied, so to speak. It has no implementation whatsoever. So the general idea in Java is that a class can inherit from as many interfaces as you like, but from at most one class. Now, in some cases, this solution might appear reasonable and sufficient, but in fact it's not. And we can see why by considering again the example of multiple inheritance of a moment ago, integer and real inheriting from both comparable and numeric. Let's start writing class comparable. And the point is that at first it might seem like an interface in Eiffel terms, a completely deferred class might be good enough, but in reality, if we try to write it for good, we're going to see that we need a real class. So let's start writing class comparable. Clearly, it's going to be a deferred class because it describes an abstract concept. We're not talking about a specific set of operations, a specific order relation, but about the general notion of an order relation. So we're going to start with a feature less than, which here I'm just calling less, with an alias less than. You remember, I hope, this convention, this technique of associating an operator with a feature, a function. And what's important here is that less is deferred. So it takes another comparable x and it returns a Boolean telling us whether the current object, the current comparable, is or is not less than x. So far it would seem that a Java-style interface would be enough because everything is deferred, and indeed we want less to be specified by the descendants of comparable, each in its own way. However, if we go further and start looking at the other operations which are fundamental in a class like comparable, like less equal, then we see that the situation changes. What is less equal? Less equal applied to A and B is going to return true if and only if A is either less than B, as defined by less, by the first feature, or equal to B. So that's what the do clause of less equal here tells us. The result is going to be true if either the current object is less than x or the current object is equal to x. This sign here, this symbol, is object equality, current equals to x. So what's really important here is that this feature, less equal, should not be deferred because the implementation is fixed, it's frozen, it's the same for every possible comparable type. Once we have less, then we have less equal through this definition. So it would actually be a design mistake not to make less equal effective, implemented as here, and to let every descendant implement less equal in its own way, because it would mean that each descendant first could make errors and could also depart from the standard semantics implied by the notion of less than or equal, that is to say, A less than or equal to B if and only if it's less or equal. So we really want to have this implementation not repeated in every descendant, and we know that repetition is always bad in software and writing programs, but we want to have it captured once and for all at the level of class comparable. Same thing for greater than. A is greater than B, of course, if and only if B is less than A. Same thing for greater than or equal. So you see what we have here. We need the flexibility of a deferred class that is not completely deferred. A deferred class which leaves a fundamental feature, in this case less deferred, and which expresses some, or in this case all of the others, in terms of that one, so that a descendant of class comparable, for example integer, for example real, for example string, only has to define, the technical term is effect, the version of less that is appropriate for integers or for reals or for strings or for whatever particular kind of comparable we're looking at. So in a situation like this, we see that the class comparable should really be a class. It's not good enough to have an interface. And the same reasoning would apply to numeric, which is why we really cannot work properly without the full-fledged mechanism of multiple inheritance for both classes, deferred and not. Last observation in this introduction to multiple inheritance, no new construct or concept, just a typical pattern, a typical idiom, which you will find often in Eiffel libraries, and which is not to everyone's taste, so you don't actually have to use it in your own code if you don't want to, but let me present it to you because we have found it to be quite useful. You find it in classes like arrayed list, which inherits, as you can see, from list and from array. Arrayed list represents a list, a notion of list implemented by array. So conceptually it's a list with elements 1, 2, 3 and so on. It's a sequence of elements, but in terms of implementation it's actually implemented by an array, which gives us an efficient implementation, at least for some operations. It makes insertion a bit inefficient, but for example element access is very fast. When we study data structures, we're going to see much more precisely how arrayed lists fare with respect to various operations. So an arrayed list is a list and is an array, which is why we have arrayed list inherit from list and from array. Now it is a list and it is an array in different senses of the word is. That is, it's a list in terms of its specification, it's an array in terms of its implementation. So that's why not everyone likes this style, because it uses inheritance for two different purposes. And if, the way it works is typically like this. This is a typical implementation of a feature of arrayed list. Ith is a feature of list, which returns the element of index I, where I is the argument. And how do we obtain the ith element? Well, since the list is implemented as an array, we just obtain item of I, where item is a feature of class array. It's the feature that gives us the element at position I of the array. So as I said, not everyone likes this because it's a bit asymmetric in its use of inheritance, but it works. So the people who don't like it, and it's a respectable trend in object-oriented programming, say, well, we should really use what is known as delegation. What does it mean to have delegation? It means that instead of considering an arrayed list as being a list, we simply say an arrayed list is implemented as a list, so we give it, in the implementation of arrayed list, we give it a field, which, as you can see, we call rep in this implementation, and that field is a reference that denotes an array. So we have an indirection. Instead of considering that an arrayed list is an array, as in the previous technique, remember that inheritance is always is. Instead of that, with the delegation technique, we consider that an arrayed list has an array. And the has relation corresponds to the client relation rather than inheritance, and it's represented here by the presence of this attribute rep. And so to obtain the same effect as before, let me show you again how it worked for the inheritance technique. We consider the arrayed list as an array, so we could directly use the feature item of array on the object itself, because the object is an array. With the delegation technique, we have a different convention, because the arrayed list is no longer an array, but it has a feature rep of type array, so we can use, as you can see here, rep.item of I, which gives us the ith element of the array rep as illustrated in the figure, position I here. By the way, you can also write this as rep of I. I used item for symmetry with the previous technique, but of course to access arrays, a synonym for rep.item of I is rep of I in brackets. So you have your choice between those two techniques. It's interesting to note, by the way, that if you are using inheritance just for implementation purposes, as we're doing here, well, there's nothing wrong with it, but it is different from subtyping users of inheritance, and in particular, it doesn't support polymorphism. If you want to exclude polymorphism, that is to say, if you want to exclude the possibility of assigning an arrayed list to an array, you can achieve this very simply by writing inherit none instead of just inherit. So you can have several inherit clauses as here, and any of them can be labeled inherit none, meaning that no polymorphism is possible. And in the graphical convention, you can see that we represent such forms of inheritance with this little special symbol in the arrow. We talk about non-conforming inheritance. The consequence of writing inherit none is that in this case there is no polymorphism. So if you have a list variable, you can assign an arrayed list to it, but if you have an array variable, you cannot assign an arrayed list to it. So this concludes the introduction to multiple inheritance. What we've seen is that this mechanism makes it possible to combine abstractions. This is a really powerful technique, and there is no reason not to take advantage of it. It's a fundamental technique for modeling systems and for constructing systems. We've seen that we have more flexibility than before, thanks to the use of non-conforming inheritance when we want inheritance but don't want polymorphism. Now, you may have noted that I haven't told you everything yet, because name clashes may occur. What if I inherit from a class B and from a class C, and both of them have a feature called F? Well, this is known as a name clash. It's not such a difficult issue if we handle it right, and that will be for the next sections, where we will study a few more details of the multiple inheritance mechanism.